Mene zelo veseli, da imamo danes v naši sredini profesor Denisa Nobla, ki ima kar nekaj, ko bi rekel, zaslug za to, da mi danes govorimo več o sistemski biologiji. Kot pionir je že leta v 60-ih, 70-ih letih predstavljal prve modele sistemske biologije, prvi virtualni organ, virtualno srce. Med njegovimi nazivi, ki jih ima, je tem, da je komtur viteškega reda britanskega imperija oziroma Commander of the British Empire, član je kraljevega združenja, član Akademije medicinskih znanosti, častni član kraljevega zdravniškega druženja. Po diplomi na Univerzitetnem koledžu v Londonu v 60-ih letih se je začel ukvarjati z samo elektrofiziološko obravnavo srca, ki je pripeljala potem do postavitve tega prvega virtualnega organa. Kot zaslužni profesor deluje kardiovaskularne fiziologije, deluje na Univerzi v Oxfordu v Veliki Britaniji in je zaslužni član koledža Balliol. Mene zelo veseli, da je predsednik Mednarodne zveze fizioloških znanosti, kjer sam delujem kot član sveta, in da je tudi eden avtorjev prihodnosti razvoja fiziologije, ki bo mogla zdaj praktično prijeti v roke določeno delo, ki ga je zamudila v zadnjih desetletjih, ker je po svoje popustila trendom redukcionizma, da so predaleč celo pripeljali določena spoznanja, ki so obljubljala rešitve mnogih bolezni, ki pa jih ne bo. In to zdaj po 10 let potem po odkritju, po razkritju človeškega genoma, je to pač postaje jasno, da so bile te obljube tudi politično vzete dosti prekmalu. Avtor je več kot 350 člankov v znanstvenih revijah. Avtor ali urednik je sodeloval pri pripravi vsaj 10 knjig in zadnja med njimi Glasba življenja, ki je na 6. do 7. mestu med svetovnimi jeziki, v katere je bila prevedena, za kar smo tukaj zelo veseli, v kateri kot pronicljiv fiziolog in filozof piše o težavah redukcionizma sodobne biološke znanosti, dvomi v centralno dogmo in vse metodologije znanstvenega raziskovalnega dela, ki iz tega izhajajo, in seveda predlaga rešitve, ki jih ponuja sistemski pristop. Dear Professor Noble, I would like to invite you to present your work here today, and we have about 40 minutes, and I hope there will be questions from the audience later on.
Marianne, hvala. I wish I could continue in your language, and I will have to ask you to excuse me for speaking in English. Your Excellency, President, ladies and gentlemen, I want to start my talk with commenting on three aspects of the very interesting speech which the President just made to us. You, sir, defined life as a dynamic network of processes. This was the English translation of what you said, and I hope it is the correct translation, because that is precisely what I am arguing for in my little book, The Music of Life, and I'm delighted that that has just been translated into the Slovene language. It's the 7th language into which it has been translated. Because, as Professor Rupnik has also emphasized in his introduction, we are at a very interesting stage in the development of physiological science. We have burrowed down to, as it were, the periodic table of biology, which is the genome. And we have discovered that it isn't what we thought it was. I'm going to say something about that in my talk. If life is to use your phrase, a dynamic network of processes, then you cannot understand it by simply looking at the components of life. Moreover, if instead of looking at life as a set of reductive components, the genes, the proteins, the membranes that make living systems in their structure, then you automatically do something else which the President referred to, which was to link genetics and genetic aspects of biology with the development of culture. And you cannot do that if you think life is a mechanism that is simply determined by the genes and proteins. I'm delighted, incidentally, to see that later on in this conference you will be hearing a talk from Eva Jablonka. She and Marion Lamb have published some of the very best analyses of the changes that are occurring in biology as we move from a very simplistic interpretation of the Darwinian idea of evolution, very simplistic because it ignores very many aspects of what Darwin himself said, to realizing the richness with which transmission of information occurs down biological systems. And that leads me to the third of the remarks of the President that I want to comment on, which was the dangers of genetic determinism. And you could say that my talk today is going to be about precisely those dangers and why we have to avoid them. So the question in my first slide is, what actually makes us human? And when Oxford University Press was looking for a cover for my little book, The Music of Life, it found this beautiful picture by a Japanese paper artist, Hideharu Naito. And the question is, what is it? Is it an insect? Or is it a violin? And of course, the Japanese paper artist deliberately required that it should be both. But notice something else. It is being played. There is a bow playing it. But there is no player. There is no conductor. One of the other messages of my book, and it also comes from regarding life as a system of processes, is that there is no central conductor. It is a system of processes that has come together through the evolutionary mechanism. So, let's deal with the question of genetic reductionism. The great prophet, of course, of genetic reductionism is my Oxford colleague, Richard Dawkins. And what I'm going to do at the beginning here is to use the central statement in his book, The Selfish Gene, published just about 35 years ago, in which he wrote, now they, of course, are genes. They swarm in huge colonies. We have the picture of a host of locusts, a host of flies, safe inside gigantic lumbering robots. For those of you who have not read The Selfish Gene, that, of course, is you and me. Sealed off from the outside world, that is the central dogma of molecular biology, which has been seriously misapplied in very many aspects of biology to suggest that somehow the genetic code is completely isolated from the rest of the system and from the environment. It is just not true. Communicating with it by tortuous indirect routes, manipulating it by remote control, that is the genetic determinism. They are in you and me. That is true. I'm going to perform, before I finish this statement, I'm going to perform an experiment on you. Because in my next slide, I'm going to turn this set of metaphors, very colorful metaphors, completely around 180 degrees to state precisely the opposite. And the experiment is this. The challenge is to think of any biological experiment that could distinguish between the two statements. So think about it while I go on. So I continue. They created us body and mind, genetic determinism again. And their preservation is the ultimate rationale for our existence. And in case you didn't understand The Selfish Gene, what Richard Dawkins wrote in a later book, The Extended Phenotype, was that readers should imbibe the fundamental truth that an organism is a tool of DNA rather than the other way round. Now let's perform the experiment. In my little book, I choose to use the metaphor of genes as prisoners. Now that is a choice. You can make your own choice. You could discuss cooperative genes if you like. You can use all kinds of metaphors. The point of metaphors in science, of course, is that they convey an ideological viewpoint. They are not necessarily what the science itself dictates. The point, therefore, of choosing an opposite metaphor is not necessarily to convince you that this is the one that is justified by biological experiment, but to jolt your thinking away from the determinist agenda to a very different view of life. So let's see what happens when we turn each of those statements through 180 degrees. Now they are trapped in huge colonies, locked inside highly intelligent beings. That's you and me. At least I hope that is the case. Molded by the outside world, I have reversed the misapplication of the central dogma of molecular biology, communicating with it by complex processes. This returns to your definition, sir, of life as a system of processes, through which blindly, as if by magic, I put that in because, frankly, we don't yet understand it. A human emerges from a fertilized egg after 9 months. Do we understand that process? The answer is no, not yet anyway. They are in you and me. That's the only statement I've not changed. We are the system that allows their code to be read. And their preservation is totally dependent on the joy we experience in reproducing ourselves. And for good measure, notice it's our joy, not theirs. We are the ultimate rationale for their existence, and you can, of course, if you wish, reverse the statement in the extended phenotype. The fundamental truth is that an organism is the only tool by which DNA can express functionality, by which the book of life, if you like that metaphor, can be read. DNA alone is inert, dead. Now, I've given this lecture to tens of thousands of people around the world, and I've always put out this challenge to the audience. Can anybody stand up and say, yes, Professor Noble, I know an experiment that will determine which of those statements is correct? I'm looking around this hall and I don't see anybody putting their hand up, and I'm not surprised because there is, of course, no way in which you could perform a single decisive experiment in biological science that would give you the difference between those two views. And you don't have to believe me. Richard Dawkins himself says exactly that. In the extended phenotype, he wrote on page 1, the vision of life that I advocate, but why did he advocate it, is not provably more correct. I doubt whether there is any experiment that could be done to prove my claim. We have been misled for 35 years about the nature of biology. The idea of the selfish gene, therefore, is a metaphorical polemic. It is not science. So let me tell you a story from my book. This is from chapter 2, and I call it the story of the Chinese emperor. And the story goes that it might have been the first emperor of China, Qin Shi Huang, who 2,200 years ago united China into the huge country that we know it to be today. And he must have fought, and indeed he did, many bloody battles in order to achieve that political success. There was a huge price and cost, of course, in terms of human life, and some of you may have done, as I have done, to visit the extraordinary tomb and the excavation of the tomb near Xi'an in China, the ancient capital of China, where those thousands of terracotta soldiers that defend his tomb are to be found. Now, my story is that one of those battles, the emperor nearly lost his life, and one of his soldiers was a poor farmer. And the poor farmer was in the right place at the right time when the soldiers in the battle led to the emperor being cornered and nearly killed until one of the soldiers, it was the poor farmer, jumped in the way and saved the emperor's life. What does the emperor do? He invites the poor farmer back to his palace in order to reward him, and the farmer turns up in the palace to see the emperor on his throne and bows down before him. The emperor says to him, "You saved my life. Have a look around in my palace. I will give you anything you wish." So the farmer looks around the palace with all its treasures, and he says, "Sir, can you bring out your chessboard?" Of course, the emperor has many elegant chessboards made of ivory and gold and so on. So he asks the courtiers to bring out the most expensive chessboard in the palace. The farmer takes it and immediately plonks it straight on the floor. And he feels inside his pocket. And he takes out from his pocket a few grains of rice. There happen to be 15 in his hand. And he approaches the chessboard, and the emperor stops him. He says, "You're not going to throw the dirt of your pocket on my magnificent chessboard, which I'm going to give you as your reward." The farmer says, "No, sir, but watch carefully." And he takes one of the rice grains and he pops it on the first square of the chessboard. He then takes 2 more grains and he puts it on the second square of the chessboard. The emperor is very puzzled. He thinks this man very clever in battle, but he's an idiot. He's obviously using his chess grains as his rice grains as chess pieces. So he commands the courtiers to go to find the most elegant and artistic chess pieces in the palace, and he says to the farmer, "These also are your reward." Farmer ignores him and proceeds to put 4 grains of rice on the next square. And if you remember, he had 15, so there are 8 left, and he puts the remaining 8 with the dirt from his pocket on the 4th square. And he turns to the emperor and he says, "Sir, I'm just a poor farmer. Your elegant chessboard, your beautiful chess pieces are of no use to me. What I would like to propose to you is this. If you will continue putting rice grains on the chessboard, as I've just done, and continue the series, when you get to the 64th square, I will just take the rice grains. You can keep the chessboard and the chess pieces." The emperor thinks the man is an idiot, but still he commands his courtiers to go back into the store of the palace to bring a 200-kilogram bag of rice. Takes 4 men to bring it and to plonk it on the floor of the palace. And a little bit angry because they're being asked to carry out this menial task, they start to put 16 on the next square, 32 on the next square. Some of you are mathematicians will have already seen where this is leading to. 64, 128. And by the time they get to the second row, they are putting thousands of rice grains onto each square. So one of them has a brilliant idea. He makes a scoop so that he can take 1,000 at a time and pour those. But actually, even that is difficult, because by the time they get to the end of that row, they need 30,000 grains. There isn't enough space on the square of the chessboard, so they start piling the rice up on the floor, noting to which square on the chessboard it belongs. It gets worse, though. By the time they've doubled each one, they get to 3 million in the third row, and the whole of the 200-kilogram bag of rice has disappeared. They look at the emperor. Anyway, one of his most beautiful concubines has just entered the room, so he's already lost interest, and he says, well, it doesn't matter, go and get another dozen bags of rice, because we had a marvelous harvest. So down they go and start counting away. And of course, by square 36, if you've done the calculations, all the rice in the palace, even if they had tens of thousands of those 200-kilogram bags, would have gone. Worse still, by square 50, all the rice in China would not suffice. And by square 64, they would be covering the whole surface of the world knee-deep in rice. The farmer looks at the emperor and says, I think you understand, sir. Even you, the most powerful man in the world, does not understand the full nature of the world. I will just take all but the last of the bags of rice. You can keep that to feed your family for another year. Now, why do I tell this story? It's because if we look at the genome, you see, what I'm going to do is to say we haven't just got 64 squares, we've got 25,000 squares. That's the current estimate of the number of genes in the human genome. So is it that the genes determine what happens? Let's do a calculation. I'm going to assume that each biological function, each process, to use the phrase that was used earlier on, depends on just 2 genes. That, of course, is an absurd idea. Contrary to what you might hear in the media and in popular newspapers, there is no gene for one particular function. There's no just one gene that creates a function. Genes have to cooperate in producing any kind of physiological function. 2 is too few, but still, the total number of possible functions, you can do the mathematics, it's easy. It would be 300 million. That is the number of strains of mice to do double knockouts that we would need to perform if we wanted to systematically work through the whole genome and do double knockouts. Why would you need to do double knockouts? Because most knockouts don't reveal the function. Why don't they reveal the function? They don't reveal the function because each function, particularly important functions like the pacemaker of the heart on which I work, is backed up by other systems. You knock one out, the system continues to operate because nature has a way of finding another process that can be used to deal with that system. Of course, if you knock out too many, you'll be in trouble. So let's take more realistic assumptions of the total number of genes involved in a function. When I model the heart, I do so with anything up to about 100 components, various proteins and other components in a cell that contribute to the beating of the heart. If we do that, we get around 10 to the 300. And if you consider any possible combination, you get this ridiculously large number, 10 to the 70,000. Now, this is getting into numbers about which we can have very little conception. Just how big are they? 10 to the 70,000. Let's compare it with the largest object that we know, which is, of course, the universe. If we allow Hubble to look at a region of space that is almost empty, in fact, it looked at a region of space which is just about 1/1,000,000th of the sky, with just about 4 stars in that region. The idea was to do a deep field view, collect data over several days, and some of you will know the beautiful images the deep field images produced by the Hubble telescope. If you leave Hubble to look at that region of the sky for just 5 or 6 days, what you find is that the sky is not empty. Thousands upon thousands of galaxies, not stars. Each of these has tens of billions of stars in it. And if you leave it for another week or so, collecting information from that region of the sky, tens of thousands of more galaxies appear. This is just 1/1,000,000th of the sky. We can actually, from the observable universe, calculate the total number of atoms or elementary particles, it doesn't matter really which you take, that there might be in the universe. Remember that figure, 10 to the 70,000. Which do you think is bigger? The surprising answer is that the total number of atoms in the universe is only about 10 to the 80. There wouldn't be enough material in the whole universe for nature to have tried out all the possible interactions, all those conceivable processes, even over the long period of billions of years of the evolutionary process. We are not, therefore, going to understand biological systems by taking that genome and imagining that we could second guess those billions of years of evolution by somehow mathematically, or how, reconstructing bottom up the human from the genome. And of course there's another very important reason why that is the case. We don't only inherit our DNA. We inherit the whole of the fertilized egg cell. And what is emerging in many of the studies, some of which you'll hear about later in this meeting, is that effects that are not transmitted simply through DNA do go down through the generations by various mechanisms in addition to the genetic mechanism. I'll just quote one example that is, I think, rather surprising. Scientists in Wuhan in China have managed to make a cross-species clone that develops to the adult. That's very surprising because most cross-species clones don't work. You get early development, but then it, as it were, freezes at an early stage. There is obviously some incompatibility with the information in the fertilized egg cell and in its nucleus, in its DNA, when you do a cross-species clone by putting the nucleus of one organism into the fertilized egg cell of the other. And that itself tells you that there is more than the nuclear DNA that is inherited from our parents. They did this as a cross-species clone between a carp and a goldfish. A carp is a fairly long fish. The goldfish, of course, is scrunched up. They are different from different genus, although from the same family. The carp has about 36 vertebrae. The goldfish has about 24. It's scrunched up. You put the carp nucleus into the enucleated fertilized egg cell of the goldfish. What number of vertebrae do you think you get? If the DNA determinist story was correct, you would get the carp number, and you would get a carp. You actually get the number that is appropriate to the goldfish. It's the first such cross-species clone that has revealed that important fact. Now, actually, it's not something that is totally new. So-called maternal effects in transmission down from the mother onto the genome of the embryo have been known for a very long time. This is just one of the most dramatic examples of that. So I want to finish, before we lead on to questions, with just one more story. Because in addition to the fact that we inherit more than our DNA, there's something else that is very important. A large amount of what happens is not coded for in genes. The earliest organisms almost certainly had to be ones with a cell membrane. If you don't have a membrane enclosing something, you don't have an individual, you've just got a soup. So I've got my last story, which I call the story of the French bistrot omelette. And the story is very simple. It is that this bistrot outside Paris was famous for the great lightness of the omelettes that the mother of the house made. Delicious, fluffy omelettes. So when the Parisian chefs were writing a new version of Larousse Gastronomique, the great compendium of French cuisine, they thought they must include the recipe of this omelette in their compendium. So they wrote to the mother of the bistrot and said, could you kindly send us the recipe? And she writes it out in great detail. Each milligram of component that is wrapped into the omelette to flavor it. And so they go to their kitchens, the Parisian kitchens, to try out the recipe, and it doesn't work. So puzzled, they use various different omelette pans and still doesn't work, so they do the obvious thing. They go off to the bistrot to see how the mother makes the omelette, and they found that sadly the mother has died, but the daughter is there. So they command an omelette, and out on their plate comes the delicious, fluffy omelette. Terrific, heaven. So they say to the daughter, were you following the same recipe as we followed? The recipe your mother gave us? She's absolutely down to the last milligram. Absolutely exactly the same recipe. She said, well, okay, can we come into your kitchen and watch you make an omelette? I said, no problem at all. And they are utterly astonished with what they see at the very beginning. Because instead of breaking the eggs into the dish to mix them up, she uses two dishes into which she puts the yolks into one and the whites into another, and she proceeds to mix all the ingredients with the yolks, and then she fluffs up she beats up the whites to form a very stiff meringue, and then she folds the meringue into the yolks, and she cooks the fluffy omelette. The chefs look at her and say, but your mother didn't put that in the recipe. And she looks at the assembled company of Parisian chefs, and she says, and how else do you think anybody makes a bloody omelette? Of course, she learned how to do it from her mother, and that's the way she makes an omelette. And I tell you this, Mother Nature knows how to make omelettes. If I tell you that you can take a few equations and develop the structure of a flower, you don't necessarily need to have all of that coded in the genes. There are structures which exist in nature, which nature has serendipitously in one way or another discovered during the process of evolution, and it would be as pointless having all of that encoded in DNA as it would be to have the properties of membranes and water coded in DNA. Membranes and water are absolutely essential to life, and the detailed properties of those components of life are absolutely essential for living systems, but they're not coded for in genes. So my message to you, and this is the point at which I want to conclude my talk and see if there are any questions, is that indeed, as you said so in your presentation, life is a system of processes. And to reduce it simply to the genome is to make the mistake that the genome is the program of life, to use another popular metaphor that was popularized by Jacob and Monod around 40 years ago. It isn't. It's a database. It's a database that simply allows the catalog of proteins, if you like, because that's what it is, to be passed down from one generation to another, and in the process of interpreting it, each life develops itself and is, of course, unique. And you don't need to believe me on this. If you read the leaders of the Human Genome Project, Craig Venter says exactly that. What I have discovered, he says in his book, is, after sequencing the genome, that life is not DNA alone. You might have to ask whether he needed to spend $1 billion in order to find that out. John Sulston, who led the English effort at Hinxton in Cambridge, says exactly the same thing. In fact, he includes in his book some of the calculations that I've given you today. Life is more than DNA. Thank you very much. Fala.
Thank you, Dennis, for this beautiful talk. I would now call the audience if there are any questions. Do I see some hands at the back? You had? No. Maybe I just start the floor with a question that might concern a little bit the financing the science in future. I think that's one of the reasons why Craig Venter and his colleagues could spend $1 billion on things, because a lot of industry saw immediate interest in the results of their work, and the promises that have been made actually were very short term.
Yeah.
So when we start to approach life in a more systemic way, so who will support that?
That's a very good question, and I think you're right, Marianne, in a very important respect, which was that the support for the Human Genome Project by the governments and charities involved, because in the case of Britain it was largely the Wellcome Trust, of course, the charity that funded it, that was largely produced because people believed the statements made by the leaders of the Human Genome Project that within 10 years, that was the statement, we would have cures for diabetes, cures for cancer, cures for heart disease, cures for aging. We would simply find out what went wrong in the genome, put the right gene in, and it would work. Where is there a single example of that having been done? 10 years later, it hasn't happened. Now, I want to make it clear, I am a total supporter of the idea that it was important to sequence the genome. That was a major technical achievement of biological science, and what it has given us by way of fundamental knowledge about biological science in terms, for example, of comparing different species, filling in many of the gaps in our knowledge of evolution, all of that is great fundamental science. But you're right, the difficulty is that if the claim had been, we want to make a great fundamental scientific discovery, would it have raised the money? I don't know. You know, the physicists raise money for the Big Hadron Collider, and largely on the grounds that it is important to know about the fundamental particles, and I think it is. So we can't be certain what would have happened. But to come to the question of systems, could that be sold to the industry? I've been doing that. The work that I and my colleagues have done have led to the developments of 2 new treatments for heart disease. One of them is ivabradine, which is a cardiac slower developed by Servier. They followed up a lead in one of the targets that we identified, and in which we also showed by a systems biological calculation could be a safe target to go for. It was a totally new target for the drug industry. Another is ranolazine, a multi-action drug, and therefore you need systems approach to understand how it works, where we helped the American company to take it through the process of it being taken to the Food and Drug Administration. I think, therefore, that systems approach has already demonstrated its commercial and health applications. I wouldn't find it difficult to sell the idea. Now, whether the pharmaceutical industry would fund it or whether governments would fund it simply because they see the importance of the eventual spin-off, I can't say. But it seems to me that it's very important to argue for this, because having got down to the bottom of the system, as it were, the components of life, the genes and proteins, almost everybody, even amongst those who were sequencing the genome, would now agree that the secret now lies in working out how they interact. And so I would say there's no alternative. We've got to go out there and convince people, industry, governments, charities, that this is worth doing.
And I think it's also a job of general education of biology to educate people that also the guys with money who have practically very short attention span would understand what the system biologists would try to tell them.